All right, let's go ahead and try to get this started. This is the first test stream of chemistry tutorials. Hopefully it goes well. I'll be keeping an eye on the chat and everything like that. And so, welcome to those of you that may be new to Twitch or new to streaming. So hopefully this will be a good experience. And so I'm going to switch over so you will be able to see me and my screen. So, howdy class. So today is just kind of a test stream. We're going to kind of see how this goes and how people respond to it and see whether this is a good way to do tutorials, because I'm trying to find different alternatives and stuff like that to work on to try to communicate stuff out. And so let's see how this goes. And if it goes well, then we'll keep doing it like this, and hopefully y'all can get the review material y'all need for IB chemistry for the mock exams and the actual IB exams. And so hopefully y'all enjoy. Make sure you stay active in the chat if you got questions and stuff like that. I think it's on like a 5-second delay, so I should see stuff pretty quickly. And excuse me. So I will be doing that. And so yeah, everyone should be able to chat in the stream chat. Just type in whatever questions you have. Oops, did this? Oh, it went on rest. I really need to. I'm going to change that right now. I need to. The display keeps going off way too often. Auto lock. We're gonna do 15 minutes. Okay. But so let's give this a shot and kind of see how this goes. Sorry for those of you that are here for gaming. That's not what this is for tonight. And so, yeah, I wouldn't watch, because unless you're in IB chemistry, this doesn't really apply to you. Actually, I guess if you're in 10th grade chemistry, this might apply to you as well, because this is stuff we're reviewing from 10th grade chemistry as well. So if you are new to Twitch and you create an account, make sure you hit the follow button in the top right. Following is free. I think you just click on the heart. That's completely free. You can set up notifications and things like that. And so you can be notified when I go online for these tutorial streams and things like that. So hopefully this will be beneficial. And yeah, this is another way that we can kind of do tutorials. I think it's easier from the comfort of your own home to kind of do this material. And so let's go and get started. Okay. So what I have set up here is my webcam and then my iPad. And so kind of like my lectures in class, I'll be using the iPad on the screen, doing notes and jotting stuff down. And I will make these notes available as well. I'll probably put a link in the YouTube video when I upload this, so that way you can, if you want to download a PDF of these notes, you can. I like to color code a lot of things, so you'll see a lot of different color coding, and that way you can kind of separate kind of concepts and ideas and stuff like that. But so at one request, just for a test stream, I thought stoichiometry might be a good one. You know, it kind of applies to 10th grade and 12th grade IB chemistry. It's a kind of fundamental thing that you have to know how to do. And so I figured this would be a good starting point, and not everyone needs to listen to this. You kind of listen to it in the background and just kind of see what's going on and stuff like that. And so really, stoichiometry is one of those things that you can do in 3 different ways, or like a lot of different ways, to be honest with you. I kind of have figured out throughout the years of teaching it that there's kind of 3 ways that students tend to like how to do this. And I don't care which way you do it, but I want to make sure that you understand the way you do it. You know, chemistry is a lot about not just memorizing a process, but trying to understand the process, because no 2 questions are alike. And the IB or any test is going to try to find a way to trick you, quote unquote, trick you. And so they'll put a twist on it. And if you don't understand what you're doing mathematically, and you don't understand how to manipulate the process that you've been doing the whole time, then you're going to struggle. And so that's kind of where stoichiometry, you need to go do with what you're comfortable with, what you're used to, whether it's in math, whether it's just the way you like to visualize things. It's really kind of important. And so I'm going to show you 3 different ways to do this that I found are kind of the three ways for to solve stoichiometry. So we'll do easy problems, and then we'll kind of work our way up to this. And so kind of fundamentally, I think it's really important to kind of establish what stoichiometry is. And stoichiometry is calculations based on ratios in reactions. That's not an official definition, but really that's what it is. And so what you care about in stoichiometry is how you go from one substance in a reaction to another substance in a reaction. Doesn't matter what units are, doesn't matter what you start with and what you want to end up with, it's still the same process throughout. And so what you'll do is use conversions, and you will find a way to convert between one thing to another. And so really the main things that you want to focus on are those conversions. No matter which way you do it, whether you do the first way, second way, or third way that I do it, you have to think about these conversions because they're used in every single format of which whatever way you do stoichiometry. And so these are the main things that I want you to focus on. I want you to focus on the concept of Avogadro's number. Okay? Which means that 1 mole is equal to 6.02 times 10 to the 23rd particles. Okay? Particles can be atoms, molecules, ions, formula units, whatever you want it to be, because a mole is just a counting number. So it just represents a large amount, like a dozen or things like that. And so it doesn't matter what the unit of particles is. It could be anything. It could be grains of rice. It could be pencils, whatever. It's 6.02 times 10 to the 23rd of that. So 1 mole of something is 6.02 times 10 to the 23rd of them. The second thing you want to focus on is the concept of molar mass. Okay, so molar mass is the concept that for 1 mole of any substance, it's equivalent to a certain number of grams. And you get that from the periodic table. And so you're using the periodic table to calculate the molar mass. So that's another conversion that you're going to focus on. Okay, you're also going to focus on the concept of let's see, I'll save molar volume for a little bit later, but the next one is mole to mole ratio. And that mole to mole ratio is a relationship between two different species. And that's the only relationship that actually matters, because that's the kind of central point in every single calculation that you do. Every calculation, if you go from one substance to another, will be a mole to mole ratio. You have to use a mole to mole ratio because that's the only way you can convert from one substance to another. And so the mole to mole ratio is essentially the moles of X is equivalent to the moles of Y in a reaction. And these values come from the coefficients. Okay? And so those numbers that come there come from the coefficients of the reactions. And that tells you how much something reacts to form something else in the reaction. And so we're going to start with this. We're not going to deal with molar volume. We're not going to deal with molarity yet. We're just going to kind of focus on this concept here and kind of work our way out from there. And so because I want to show you kind of the basis of each of the three ways and then kind of branch out and see how things get added on to each calculation. And so there are three ways that I find that you can do kind of calculations here. And so what we'll do is we'll start with a overall equation. So we will start with, let's say, N2 plus 3H2 yields 2 NH3. So in this equation, what they're saying is that 1 mole of N2 reacts with 3 moles of H2 to form 2 moles of NH3. And that's the ratio. And so whenever you're going from one substance to another, you're going to want to pick which of those two values that you're going to be converting between. And so let's say we have something like, I don't know, like 56 grams of N2. And we are trying to gotta get my calculator out for this. We are trying to calculate how many grams of NH3 are produced from this. Okay, so we'll just say we're trying to figure out how many grams of NH3 are produced from 56 grams of N2. One way to do it is called the factor label way. Sometimes you call it train tracks, sometimes you call it dimensional analysis, things like that. But the idea of this is to use conversions as fractions to cancel units. So what you're trying to do here is you're trying to use these conversions up here, all these conversions up here, and more that we'll add on a little later, to convert from one unit to another. Because these equivalencies up here can be written as fractions. And those fractions can allow you to convert from one substance to another. And so I'll be honest, this is the way I learned it when I was in high school. My teachers taught me this way because I think they always kind of thought that it was the way that made the most visual sense. Because when you see it laid out, you can kind of see if you've done everything right. Because all the units should cancel, and you should be done. When you're done, you should have only the units that you want left. Okay? And so you would start here with 56 grams of NH3. So having said that, you know you want to get rid of grams of NH3. So you're going to have grams of NH3 at the bottom, and that's going to be the equivalent of 1 mole of NH3. And that mass, N2. I'm sorry. N2. Grams of N2 in this. Now, according to periodic table, it is, I'm going to round to a whole number just because I want to show the process. I don't really care about the actual precision of the values right now. But in this step, you know that you're on to the right next step because there's only one conversion that involves grams, and that conversion is molar mass. So you don't have much of a choice. With factor label, you have pieces of the puzzle, and then only one piece fits each time, and so you keep using pieces until you get to what you want to. So it's kind of like a puzzle. And so here, you know you have moles of N2. Well, now, according to your equation, 1 mole of N2 makes 2 moles of NH3. So therefore, again, your units cancel out, and you're left with 2 moles of NH3. But you want grams of NH3. So 1 mole of NH3 is equal to 17 grams of NH3. And so if you notice, the units cancel out, so that way the only units you're left with are grams of NH3. And so piece by piece, you've been able to knock out units until you get to the final way. What's nice about this is you don't have to memorize whether you multiply or divide things because the fraction only can be set up the way so that it's correct. So there's less kind of developing relationships because you don't really have a choice in the way you do it. And so I think that's why I was taught this way, because the teachers always thought, okay, what's the way that you can do this where there is as little room for error as possible? Because it's all in one line. You can check all your units, make sure they cancel, and you can see how things kind of divide or multiply. And so everything on the top you multiply by, and everything you divide by on the bottom. And so that's how they did it. Now, I get why students don't like this, because it's just multiplying by fractions doesn't seem like you're really kind of converting anything. And so in math, you do a lot more proportions. And so that's where kind of the next way that students tend to do this type of problem. And so that way they tend to do is I call it the proportion method. So with these students, what they use is they use these conversions up here as one side of the proportion, and they use their unknown as the other side of the proportion, and then the one last space is the value they don't know yet. And so, for example, in this, you would do kind of small steps in between. So you would say first, well, 56 grams of N2. What conversion has grams of N2 in it? Well, the only conversion I have that has grams of N2 in it is the molar mass, because 28 grams of N2 is 1 mole of N2. Okay? And so using my units matching up in a proportion, they have to be across from each other because it's equal to each other, not like in a fraction where you multiply. And so grams are on top, moles are on the bottom. So therefore, your answer here should be in moles as well. So when you solve for that, you end up finding that it is 2 moles of N2. Now, once you have 2 moles of N2, moles are the conversion factor that you need to use to go from one substance to another, which is the mole to mole ratio. And so you see that 1 mole of N2 makes 2 moles of NH3. And then, therefore, if you solve for this, you should be able to end up with the moles of NH3. And you cross multiply, as you do in proportions, and you end up finding that you have 4 moles of NH3. Okay. Now, with moles of NH3, you can then go to grams by using the molar mass as well. But notice that I write it a little bit differently because my units across have to be the same. So here it's 17 grams of NH3 on the bottom, so I can solve for grams of NH3. And so what I end up getting is, 68 grams of NH3 I can make. Okay. And if you notice in the factor label, you're doing the same steps. All these ways that you're calculating, you're doing the same steps. And so it doesn't matter. You should get the same answer no matter which way you do it. Up here on the top, I forgot to calculate it. 58 divided by 28 is 2. Times 2 is 4. Times 17 is also 68 grams of NH3, sorry. Okay. And so this is kind of those ways to do it. And so these are kind of the 2 ways that I kind of saw. Now, some people that are fairly savvy will combine some of this. You know, I think I've seen some of this where if you start understanding this ratio, you can start minimizing how many steps you have to do. Because here, I've taken each of the conversions and just done one step by one step by one step. Some students may start combining steps because they realize that if I combine this step and this step and this step, I can do the proportion method in one step because these are all equivalent to each other. Because 2 moles of NH3 equals 1 mole of N2. And 1 mole of N2 is 28 grams. And 2 moles of NH3 is 34 grams of NH3. So sometimes they end up condensing it, and where they put 56 grams of N2 over X grams of NH3 is equal to 28 grams of N2 and 34 grams of NH3. And that works fine too. But you make sure that you understand why that's happening, because what you're doing is essentially combining 3 different fractions on here so that you can simplify and do one proportion. And that works too. But you really need to understand why that is. And that's only true because you can combine the grams with the moles and then make a mass to mass proportion instead of a mole to mole ratio. That's all you're doing. You're taking the mass of each substance and multiplying by the mole to mole ratio to get that mass to mass ratio. And so that works just as fine to do this. It gets tricky when you start not going from one unit to another unit. Like, let's say you're going to grams to moles. Well, then if you're going from grams to moles, you don't want the bottom to be grams, so you might write 56 grams of N2 is equal to 28 grams of N2 and then 2 moles of NH3, which then gets you to the moles of NH3. So you have to make sure that you understand the mole to mole ratio and then the conversions to be able to condense it. And so I don't necessarily recommend doing the condensed form until you understand kind of what's happening in this proportion method. But the red part makes more sense to some people because they're used to in math setting proportions, cross multiplying, and then solving for each one and going through. And that works fine. Your key thing is always to try to work toward moles, because then moles can take you to the next step. And so if you're in grams, convert to moles. If you're in moles, convert to the other moles so that you can keep going on. So you can kind of see where everything is lining up. Okay. If you have any questions, feel free to say things in chat. I'm going to try to respond to every question that I can. So just let me know if there's anything that I can do for y'all to kind of help you see what's going on. So feel free to type anything in the chat so I can respond to it. If you need me to slow down, if you want me to go over something again, please feel free to say something in chat. The third way, I've kind of adapted from something else I did before with acids and bases, but then I realized that this way actually works for every stoichiometry problem. And so I'm introducing this as a third way to do things. I'm not sure who benefits from this the most, because I feel like factor label makes sense because you're putting piece by piece by piece in the same row so all the units cancel out. Proportion method, people like that there's small proportions, kind of like math, you're solving for a piece and solving for a piece for solving for a piece. This method, I guess what's nice about this method is that it centers around the same setup every single time. And so I call this kind of the super proportion. I don't know, I'm not trademarking that name. I'm just going to call it the super proportion method here. And so it's something that I've adopted, and I think some people may like, and so I'm offering it to you to see if you think it's useful. And so super proportion method is kind of like proportion method, but instead of doing little pieces here and there, you have the same proportion every time, and your job is to make things fit into that proportion. And so what I mean is this. Every time you do the superproportion method, the right side of your reaction should be moles of A going to moles of B. So the coefficient of the substance you have going to, thank you, Nabil, going to the moles or the coefficient of the unit that the substance that you want. So, for example, in this problem that we just did, I know I have moles of N2, and I know my moles of NH3. So I have this every single time. The proportion method every single time, no matter what type of problem it is, the right side of proportion is a mole-to-mole ratio, no matter what. Okay? Your job in this format is to make the left side of the proportion moles as well, so that you can solve for it. And so there are a lot of different ways that you can plug values in here. And so there's little mini equations that you can do on the side before you plug it in here. Like you can say molar mass equals mass over moles. Or let's say moles equals number of particles over Avogadro's number. And so you can plug in whichever of these formulas that you want to do what you need to over here. So, for example, the top part for N2, I have the mass of N2. Okay? And so I could say that the top, if I wanted to solve for moles of N2, I would say, well, I have 56 grams of N2, and I want to divide it by the molar mass, which is 28 grams of N2. So that top part would equal the moles of the N2. On the bottom, I want to solve for grams of NH3. But if I do this proportion, I'm going to end up with moles of NH3. So how do I convert that? I can say, well, if I want X grams, I know that's the number of moles. And so if I divide this by molar mass, then I can figure out the grams in one super proportion. And so the molar mass is 17 grams. So now I have this giant proportion that I can cross multiply and solve for as well. And so what I end up getting here is this 2 times this 2, which is 4, is equal to X over 17. So then X equals 68 grams. And so then that conversion method works as well. And so what's great for all these methods is you can just keep adding conversions into this, and you can kind of piece by piece put things together and make them all work. So I don't have a preference for this. I guess I'm a little biased toward factor label because that's the way I was raised on doing it, but I can solve problems all three ways, because you're going to, as long as you understand what's happening, you can use any method that you want to get that. And so it's about owning that method and knowing it so well that you can tackle any problem. And so any of these three ways that you want to do a problem, go for it. And if you have questions about it and you want me to go over something that you kind of missed or you don't understand, please feel free to put it in the chat. And then say what you want me to go over, and I will do my best to kind of go over that. But so this is the most basic of stoichiometry. So using factor label, the small proportion method, or the super proportion method, all has their pros and cons. And so and figure out which one that you feel is the most useful for you. Because as you add more and more conversions, you're going to have to make sure that you can kind of manipulate those. But any of these three ways, you can solve every single type of problem that you need to. I promise you, every single type of reaction problem where you're given an amount of something and you're trying to get the amount of something else, all three ways work. And all three ways can be the same speed. There's no one way that's faster. Yes, maybe you write a little bit more in the proportion method, but kids get so fast at writing the proportion they don't even think about it anymore. It doesn't become a time hindrance, and you're not going to run out of time because you're writing a proportion. Okay, you're going to run out of time when you have to hesitate and think too much about the way you're doing it. And so, if kids don't like factor label, I don't try to push it upon them because that doubt is kind of your worst enemy. I'd rather you do it whichever way you think makes the most sense to you, and that you can explain to someone else why you're doing it that way. If you can explain that, then I don't care which way you solve for it, as long as there's no kind of misconceptions in it. But so, as you do this, you start to add a few more conversions into this. So I just did a kind of simple grams to grams one, but so you need to be aware of some additional conversions into this method. Okay, molar volume. Okay, molar volume is equal to the moles per decimeter cubed. Okay, so at STP for gases, that is 1 mole is equal to 22.7 decimeters cubed. Okay, you're probably an IB if you're watching this, so that's why we use 22.7. I know AP Chemistry uses 22.4 because their conditions are slightly different, but we are going to use 22.7 because I'm an IB chemistry teacher, and that's what I'm trying to get my kids used to. And so you can use this equation if you want to manipulate it for the superproportion, or you can use this ratio if you want to do factor label or proportion method as well. And those are always true. If it's not at STP, then you have to manipulate it a little bit, but it's not a big deal. Okay. Another one you might need to know is molarity. Okay. Molarity is the main version. Oh, Jacob, I have not done the giveaway yet. And so, Nabil, thank you for the subscription, Nabil. How do I become the top cheer? Well, you have to buy bits and then donate them to the stream. You can actually get bits for free by watching ads as well, but I think there's a limited number of ads that you can do as well. And so, NF. Who? Oh, Nico. Duh. I was like, I'm thinking through initials right here. So, yeah, I'll probably do the giveaway for subscribers. But unfortunately, Nabil isn't in this one because I promised it's only be 11. I was going to do that night, but everyone had kind of logged off already. And so, Nabil's in here. Jacob's in here. I think there are a few other people too. Some lurkers. I don't think that has accounts. And so, thank you, Nabil. I appreciate the subscription. Like I said, if we get to 20 overall, I will do a giveaway, and I'll let someone choose a video game of their choice. If you're not into video games, we'll come up with something else that that will be the equivalent for you. But so I'm going to continue on here, and then I will do the giveaway for the first 11 subs probably a little bit later on. Actually, Nico, if you link your Amazon Prime account to your Twitch account, you get 1 free sub every month. It doesn't cost you anything. And so you can subscribe to my channel for the month. It doesn't renew automatically like if you pay for it, but then you can go in and resubscribe each month. And so just letting y'all know about that. But so, sorry, didn't mean to get off topic. I know we're getting a lot of people watching in here now. So molarity is another equation that you need to be familiar with. Molarity is moles over volume. And so you're going to have some molarity. So like, let's say you have 6 molar. That's equal to 6 moles over 1 decimeter cubed. And so that's the conversion that you're going to use in your factor label, your proportion method. You can flip it upside down. You can use it this way. Whichever way you want, that's the conversion you're going to use. If you're doing the super proportion, then you're going to probably want to use this equation so that you can convert to moles. And so you're going to want to rearrange this if you're doing the super proportion. You're going to want to rearrange it to, let's see. You're going to want it to be volume times 22.7 to get moles because you're rearranging. And then you're going to want molarity times volume equals moles here. So if you want to do the super proportion method, then you are going to want to manipulate those equations that I've boxed into the way so that they're equal to moles. So that way you can plug it right into the super proportion method on the left. Okay. So let's see. Other conversions that you might have. Density. Well, yeah, I guess density I'm going to throw in there too, just in case. I mean, the IB might throw kind of a curveball here. Density is equal to mass over volume, which is usually in decimeters cubed or centimeters cubed. So it's a conversion though. So like if you have a density of 5 grams per centimeter cubed, then you write it as a conversion, 5 grams, 1 centimeter cubed, and then you can flip it whichever way you need to so the units kind of cancel out. Okay. Don't forget, guys, I'm trying to look at chat. You kind of see my eyes kind of wandering over. The screen on my left has a chat up, and so so I'm trying to keep an eye on the chat while I'm lecturing and stuff like that. Hopefully you can read the screen all right. But so yeah, we're gonna kind of keep going on this. If I had to think of anything else for stoichiometry, I think those are the main ones that you're gonna have to really deal with. I'm trying to think if there's anything else. I don't really think so. And so, yeah. So using some of these conversions can also lead you to kind of acid-base neutralization as well. That's kind of another IB calculation that you need to be familiar with. And so, again, also, I am recording right now, and so I'm going to upload this to YouTube kind of in its entirety right now. I'm not going to try to edit stuff out. So you can watch the whole live stream, so you'll get all this conversation. The thank yous and the alerts and stuff like that. But that's okay. If it gets to a point where it gets kind of too crazy and I need to edit some stuff out here and there, I will. But I don't think there's really anything that I need to edit out. And so I'll put this up, and I also link the PDF of the notes to the Twitch video. And so that way you can see the notes and kind of follow along and see what I was writing and things like that and kind of put it all together. But so acid-base neutralization is another big stoichiometry thing, okay? So here, this is a titration essentially, where you're reacting to acid with a base and you're trying to find out an unknown molarity or unknown volume, things like that. And so I'm going to do, we'll say HCl plus Mg OH2. Okay? And that yields MgCl2 plus H2O. So, to balance that, you get this equation. So what that's saying is that 2 moles of HCl react with 1 mole of MgOH2. And so, let's say I'm doing a titration and I don't know the molarity of my HCl, but I know that I used 30 centimeters cubed of HCl. And I know that molarity of my magnesium was 0.5 molar, and ended up using 24.6. I probably should write a little more significant figures here. Oops. 30.0, and we'll say 0.500 molar. And then we used 24.6 centimeters cubed of base. Okay? And I'm going to do it all 3 ways, again, so that way you can kind of see how you can manipulate these equations to solve for them anyways. And so what I generally do is I usually start, in factor label at least, is I start with a value that has no dual units. Because everything that has dual units is a conversion, which I can use later on. So I'm going to use the volume of the known first. So I know that there's 24.6 centimeters cubed of MgOH2 that's used. Now, the molarity is 0.500 moles per decimeter cubed. So I need to convert that into decimeters cubed before I can use that molarity as a conversion. Okay? And so now that I have decimeters cubed, I can use the molarity and say 1 decimeter cubed is 0.500 moles of MgOH2. Okay? And so now things are starting to cancel out. So now I know, according to my equation, that there is 1 mole of MgOH2 for every 2 moles of HCl. Okay? Now, that cancels, that cancels. Since I want molarity, I need to have moles over volume. And my unit of volume here is 30 centimeters cubed. I need that to be on the bottom. So I can actually put it in my equation as just a conversion. 1 over 0.030 decimeters cubed. I just converted it because I was running out of space, and so I just put it on there. But so this way, I end up with moles, and I end up with decimeters cubed, so I end up with molarity. And so if I do this, I get, 0.82 molar of HCl. Okay? Now, this answer makes a little bit of sense, because if let's see, if this were, well, let me make sure. 24. Okay, let me just make sure I'm saying this right. So if this were a 1-to-1 ratio and I used about the same molarity, I'd get 0.5. But this is a 2-to-1 ratio and I used a little bit more, so it's going to be a little bit more than 0.5. And 0.82 is a reasonable number for this value here. And so notice how factor label gets all the units canceled out. Okay? In the proportion method, okay, you're going to be converting, you're going to be solving for moles and then solving for the mole-to-mole ratio and then going back to that. So you'll have 3 steps in this. And so you'll say, well, first of all, the molarity of NaOH is 0.500 moles per decimeter cubed. Okay? But I have 0.0246 decimeters cubed. So how many moles of MgOH2 do I actually have? Okay? And so 0.5 times 0.0246 gets me 0.0123 moles of MgOH2. Well, 1 mole of MgOH2 makes 2 moles of HCl. So therefore, I can figure out the x moles of HCl. So my moles of HCl are 0.0246 moles of HCl. Well, that over my volume of HCl, 0.0300, gets me my molarity. And so I should get 0.832 as well when I calculate this way. Okay. So that's the other way to solve proportions. The superproportion method kind of originated from this, to be honest with you, because I was trying to find a way to simplify acid-base neutralization, and I kind of set this up, and then I realized, well, this could work for everything. And so what we did, again, the right side of the superproportion is always the moles of your known in the molar ratio over your moles of your unknown, which is 1 to 2. And your only job here is to make it so that there are moles on the left side as well. And so how do you get moles? Molarity times volume. So our molarity times our volume. And then on the bottom is molarity times volume. But we don't know molarity. We know volume. Notice here I didn't convert units to decimeters cubed because the proportion stays the same. So if I have centimeters cubed on the top and centimeters cubed on the bottom, it doesn't matter. I can use them both as centimeters cubed because the proportion is still the same. And so that's kind of a little trick here. And so when I set this up, I get 30.0 times m is equal to 24.6. So divide by 30, and I still get 0.82 molar. So all three ways work perfectly fine. I don't care, again, which way you do it. I just realized I'm wearing a Big Bang Theory shirt that I was gifted from one of my former students. And so, yeah, these are all actually elements: barium, zinc, and gallium. But, so, I don't care which way you do it. And if you have questions about this and you want additional kind of work with this, let me know, and then we can meet up and kind of work on this as well. And if there's a certain way that you'd really like to see a bunch of problems done, I can do that too, and maybe I can put it up on YouTube as well. Factor label, there's a lot of people that do factor label out there on YouTube. A lot of people do proportion. If you want to see a lot of super proportion method stuff being done, let me know, and then we can try to make that work as well. Let's see. Questions so far? Anyone have any questions about the stoichiometry process? Like I said, 3 different ways to do it, whichever way that you like the best. Okay. Let's see. Try to think. Yeah. Okay. Trying to think, there's something else I want to focus on here as well. I guess the only other kind of stoichiometry that you might kind of work in here is gas law stoichiometry, where you have to use PV. Well, you don't have to use PV equals nRT, but sometimes you do, because when you're at non-standard conditions, you need to figure out the molar volume at non-STP. So for your conversions, you may use PV equals nRT to convert to figure out what the molar volume is at non-STP, given the temperature and pressure for that case, and you just plug in N equals 1. Now remember, R is 8.31 joules per mole Kelvin for IB, and then temperature has to be in Kelvin, and pressure has to be in kilopascals, and then therefore the volume will be in decimeters cubed. Okay, and so you may have to use this equation to figure out the molar volume for you to be able to calculate between gases. Now, a little bit of a trick is that if you go from volume to volume for gas laws, you don't actually have to do all the steps, because the tip for gases is that decimeters to decimeters ratio is same as mole to mole. Okay, so you can actually skip a bunch of steps because they all cancel out. Like the molar volumes would all cancel out if you're going from decimeters cubed to decimeters cubed. And so you can see that, like, let's say for that equation again, N2 plus 3H2 yields 2NH3. If I start with 4 decimeters cubed of N2, yes, I could convert using molar volume and then say, well, 1 mole of N2 makes 2 moles of NH3, and then 1 mole of NH3 makes 22.7 decimeters cubed. Well, what happens is it just all cancels out anyways. So all you're left with is the mole to mole ratio. So you can literally just write 4 decimeters cubed of N2, and the ratio is 1 decimeter cubed of N2 is the same as 2 decimeters cubed of NH3, and save yourself a little bit of calculations there. Okay? And so, because every gas at a certain temperature and pressure occupies the same volume for the same number of moles. So the mole to mole ratio is the same as the volume, but this is only for gases. Don't start doing it with solutions and things like that. That gets a little bit tricky. But for gases, you can skip a lot of those steps and then just kind of boil it down into this. And you can set this up as a proportion method or as the superproportion method, and it still all gets you the same thing. Okay. Questions about that? Okay. Don't see anyone saying anything about that. And so, let's see. Okay. Let's see. Okay. I think that will be the test stream for today. About an hour today. Not too bad. I'm going to sign off now for the YouTube, and I'm going to stop recording, and then I will do the giveaway for the sub giveaway, and so that won't be on the YouTube. But so, thank you so much for coming to watch the stream, and if you're seeing this on YouTube, thank you for kind of watching it on YouTube. Hit the like button if you learned anything from this, and make sure you add any comments if you want to add any suggestions, possible future topics as well. I'd be more than happy to take your suggestions. And so, you have a good day. Class is dismissed.